In continuation with our discussion, so we're going to discuss Newton-Raphson method. So Newton-Raphson method is the most widely used of all root locating formulas. It is most common and most accurate root finding technique. This method involves the use of the slope of the tangent to the curve. So the Newton-Raphson method can be derived on the basis of this geometrical interpretation as in figure 6.5. So the first derivative at x is equivalent to the slope. So given the slope, so we will have here the function of x sub I minus 0 all over x sub I minus x sub I plus 1, which can be rearranged to yield the equation x sub I plus 1 equals to x sub I minus the function x sub I all over the first derivative of the function x sub I, which is called the Newton-Raphson formula. So this figure 6.5 is the graphical depiction of the Newton-Raphson method. So a tangent to the function of x sub I, that is the first derivative of the function x sub I, is extrapolated down to the x-axis to provide an estimate of the root at x sub I plus 1. So this is the graphical depiction of the Newton-Raphson method. So we have the first derivative x sub I. So we all know that the first derivative of x sub I is simply the slope. And we have here the rise over run. So the function of xi, so the rise, and it started at the origin 0. So we have here the function of x sub I minus 0. And so it is a tangential to the curve. So we will have here for the run. So we have x sub I minus x sub I plus 1. So we have x sub I minus x sub I plus 1. So rearranging this particular equation, we will be able to have the formula x sub I plus 1 equals to x sub I minus the function x sub I all over the first derivative of the function x sub I. So in this box 6.2, so this is simply the derivation and error analysis of the Newton-Raphson method. So this is how the derivation of the Newton-Raphson formula were established. So you can just try to restudy them or you can just read them because the main purpose of our study is to apply the derived formula of the Newton-Raphson method. So let's have an example. So for a Newton-Raphson method, so problem statement, use the Newton-Raphson method to estimate the root of the function of x equals to e raised to negative x minus x, employing an initial guess of x sub 0 equals to 0. So the solution, so we're going first to find the first derivative of the function and can be evaluated as this particular function, which can be substituted along with the original function into the equation of the Newton-Raphson formula. It will give the x sub I plus 1 equals to x sub I, and substituting the function of x sub I, which is the given function, so e raised to negative x sub I minus x sub I all over the first derivative of the function x sub I, so it will be negative e raised to x sub I minus 1. And continuation of the solution, so starting with an initial guess of x sub 0 equals to 0, this iterative equation can be applied to calculate and be represented in this particular table. So sometimes the table representation, nauuna ang ating approximation error or approximation percentage relative error, and nahuhuli yung ating true percent relative error. So thus the approach rapidly converges on the true root. Notice that the true percent relative error at each iteration decreases much faster than it does in simple fixed point iteration. Based on the table, the root of the function is the last value of x sub I plus 1, which is 0.5671439. Note, the obtained value of the root using this method is much more accurate than using the first two methods for the same number of iteration. Thus, this method is the most preferred root finding method. However, a potential problem in implementing the Newton-Raphson method is the evaluation of the derivative. Although this is not inconvenient for polynomials and many other functions, there are certain functions whose derivatives may be extremely difficult or inconvenient to evaluate. So in order to clearly understand how the Newton-Raphson method is applied, so let's try using Excel applying Newton-Raphson method. Using Excel applying Newton-Raphson method, so for the first iteration, so we have here the initial value of x sub 0 equals to 0, or simply the value of x sub I is equals to 0. And for the function, it will be the given function of x and substituting the value of the initial guess of 0, exp raised to negative x minus x. So this will be the value of the function. And for the first derivative, so we're going to use the first derivative function and substituting the initial guess x sub I. So this is simply negative exp raised to negative x minus 1. So for the x sub I plus 1, so applying this particular formula from the formula of Newton-Raphson, so we will have here initial minus the function all over the first derivative. And we already have the value of x sub I plus 1. And for the second iteration, so the value of x sub I will be the calculated x sub I plus 1 at the first iteration. And same process for the given function. So this is simply exp or simply e raised to negative x minus x. And for the first derivative, so negative e raised to negative x minus 1, and applying the Newton-Raphson formula by substituting the function of x sub I all over first derivative of the function x sub I, we will have here the value of x sub I minus the function of x sub I all over the first derivative of the function x sub I. And for the third iteration, so same process, the new calculated x sub I plus 1 from the second iteration will now be used on the third iteration. And same procedure will be applied. So, substituting the value of x sub I to the function and to the first derivative and applying the Newton-Raphson formula, I have here this particular result. And just continue the process until such time that the function of x will now be equal to 0. Once the function of x is already equal to 0, it just simply means that you already find the value of the root. And the value of the root will be located as the last value of x sub I plus 1. So, we're now going to calculate the approximate error. Current minus the previous all over the current multiplied by 100. And just continue this process. So, you will have here current all minus the previous all over the current, and so on. And for the true error, so we will have here the true value minus the approximate value divided by the true value multiplied by 100. And just put a dollar sign. So, we will have here true value minus approximate value all over true value. So, same. So, this is how we apply the Newton-Raphson method. So, let's try applying the simple fixed point iteration in this given function. So, simply by rearranging the function of x equals to 0, so we will have an equation of x is equals to e raised to negative x. So, this is simply rearranging the function of x which is equated to 0. So, for the iteration, so we will have here the value of the given or the arranged equation. And for the first iteration, so the value of x will be initially at 0 value. And substituting the initial value, exp raised to negative x, we already have here the value of 1. So, for the second iteration, so the value of x will now be the calculated value from the equation and simply substitute at the equation and continue the process until such time that the value calculated is not changing already. So, hindi na nagbabago. You can visually see applying simple fixed point iteration on the 41st iteration is the location value of the root according to the true value. So, ibig sabihin, masyadong mahaba or matagal bago mag-converge ang ating calculation applying simple fixed point iteration in comparison to Newton-Raphson method. So, nasa 6 iteration pa lang, you already find the value of the root of the function. So, dito nasa 41st ka pa bago mo makukuha yung mismong root of the function. So, continuing with our discussion, so we're now going to discuss second method. So, for these cases, the derivative can be approximated by a backward finite divided difference as in figure 6.7. So, the first derivative of the function x sub I is equal or congruent to the function x sub I minus 1 minus the function of x sub I all over x sub I minus 1 minus x sub I. So this approximation can be substituted into the equation in this particular equation to yield the following iterative equation. So on our previous discussion, applying Newton-Raphson method, the value finding the root is x sub I plus 1 equals to x sub I minus the function of x sub I all over the first derivative of the function x sub I. So in second method, finding the root of the function, we will now going to use the value of x sub I plus 1 equals to x sub I minus the function of x sub I plus 1 multiplied by the difference of x sub I minus 1 minus x sub I all over the function of x sub I minus 1 minus the function of x sub I. So the figure 6.7 is the graphical depiction of the second method. This technique is similar to the Newton-Raphson technique as shown in figure 6.5 in the sense that an estimate of the root is predicted by extrapolating a tangent of the function to the x-axis. However, the second method uses a difference rather than a derivative to estimate the slope. So this is simply applying or finding the slope. So we have here the first derivative will be equated function of x sub I minus the function of x sub I minus 1 all over. So the run, so it will be x sub I minus x sub I minus 1. So rearranging this equation, so we can have here the value of the x sub I plus 1 equal to x sub I minus the function of x sub I multiplied by x sub I minus 1 minus x sub I all over the function of x sub I minus 1 minus the function of x sub I. This is the graphical representation in finding the formula applying second method. So it is not using the first derivative. Unlike nung sa ating Newton-Raphson, gumagamit pa siya ng derivative ng function. So let's have an example applying second method. So for the problem statement, use the second method to estimate the root of the function equals to e raised to negative x minus x. Start with initial estimate of x I minus 1 equals to 0 and x sub 0 equals to 1. So for the solution, recall that the true root of the given function is 0.5671439. So for the first iteration, given the value of xi minus 1, which is equals to 0 or simply x subscript negative 1. So for the particular function, we will have here substituting the value of x equals to 0 to the given function, we will find the value equal to 1. And the value of x sub 0 equals to 1. Finding the function of x sub 0 by simply substituting the value of x sub 0 to the given function, we will have here the negative 0.63212. So, this will be the x sub 1 or simply the x sub I plus 1 which is equal to, from the given formula of the second, this will be x sub I minus the function of x sub I multiplied by the difference of x sub I minus 1 minus x sub I all over the function of x sub I minus 1 minus the function of x sub I. So, paano i-substitute? This will be the x sub I or simply the x sub 0. So, x sub 0 will be the x sub I and this is the x sub I minus 1 and this will be the x sub I plus 1. So, we will have here the x sub I plus 1. So, substituting the value of x sub I. So, we have here 1 minus, so the fraction of the function of x sub I at the numerator. So, this is the function of x sub I. This will be the function of x sub I minus 1. So, we have here negative 0.63212 multiplied by the difference of 0 minus 1 all over 1 minus negative 0.63212. So, we'll have now the value of x sub I plus 1 equals to 0.61270 at true percent relative error of 8%. So, continuation of the solution. So, for the second iteration, we will have here the x sub 0 equals to 1. So, this is from the value of x sub I. And for the x sub 1, this is the calculated from the first iteration, x sub I plus 1. And we now already have the resulted function of x sub 0 and x sub I plus 1. So, for the second iteration, we have here the x sub 0 equals to 1. This is simply from the x sub I. And x sub 1 is simply the resulted x sub I plus 1 from the the first iteration. So, substituting the value of x sub 0 and x sub 1 to the given function equals to e raised to negative x minus x, we will be able to find the value of the function of x sub 0 equals to negative 0.63212, and for the function of x sub 1, substituting to the function the value of x sub 1, we will have here negative 0.7081. So note that both estimates are now on the same side of the root. So for the x sub 2, so this will be, so take note class, for the second iteration, the value of x sub I at the first iteration will now become the x sub I minus 1. And the result of x sub I plus 1 on the first iteration will now become the x sub I. And the x sub 2, so this will be the x sub I plus 1. So substituting, so we have here from the given formula of the second method, so we have x sub I plus 1 is equals to x sub I minus the function of x sub I multiplied by the difference of x sub I minus 1 minus x sub I all over the function of x sub I minus 1 minus the function of x sub I. So in the second iteration, the value of x sub I will be the x sub I plus 1, which is the x sub 1, and the function of x sub I will be the negative 0.07081 multiplied by the x sub I minus 1 will be the x sub 0. So this will be 1 minus the 0.61270 from the x sub 1, or simply the x sub I of the second iteration, all over the function, the resulted value of the function x sub I minus 1. So this is simply the negative 0.63212 minus the value of the function x sub I, which is the negative 0.07081, and we will now have the new value of 0.56384 for the value of x sub I plus 1 for x sub 2. So for the third iteration, so same process will be applied. So the value of x sub 1, which is the x sub I at the second iteration, will now become the x sub I minus 1. And the x sub 2, which is the x sub I plus 1 at the second iteration, will now become the x sub I. And we're going to substitute the values of x sub I minus 1 and x sub I to the given function. So this is simply the function of x sub I minus 1 and the function of x sub I. And we will now be able to find the new x sub I plus 1 based on the third iteration, which is the x sub 3. And substitute x sub I point, which is the x sub 2, x sub I is the x sub 2, and the function of x sub I is the function of x sub 2, and x sub I minus 1 is simply the x sub 1, minus the x sub I is simply the x sub I is the x sub 2, and function of x sub I minus 1 is the function of x sub 1. The function of x sub I is the function of x sub 2. And now we will have the value of 0.56717. And it will have a true percent relative error of 0.0048% for the third iteration. And on the second iteration, we have also calculated the true percent relative error of 0.58%. So continuing of solution, the process is repeated and it will be represented in these particular final answers. And sometimes the table representation, nauuna yung ating approximate error bago yung ating true error. And the continued process, so same din kung ano yung pinaka-last value ng ating x sub I plus 1, it is also the value of the root of the given function. So in order to clearly understand how the second method is applied, so we're going to use Excel applying second method. Using Excel applying second method, so for our iteration, so before I start with the second method, I just want to make correction on the starting iteration of the Newton-Raphson. So previously, I have shown here that the iteration representation is started at 1. So in order to have a consistency with the initial guess and it is represented as x sub 0, so we're going to start the iteration for the Newton-Raphson as the 0 iteration until the last iteration wherein the approximation percent relative error and the true percent relative error is equals to 0. So getting back with our second method, so for the iteration, so for the consistency of the iteration, it is indicated in the process that we are having here the value of x sub I minus 1. So the iteration here will start as negative 1 and it will have an 0 iteration and the first x sub I plus 1. So for the x sub I, so the x sub I minus 1, it is indicated here that it will have a value of 0. And for the x sub I or simply the x sub 0, it will have a value of 1. So for the function of x, so it will be substituting the value of x sub I or simply the value of the function x sub 0. So for the function, we will have here the given function of e raised to negative x minus x. So for the function of x sub I minus 1, it will be e raised to negative x minus the value of x. And it will have a value of 1. And for the x sub I plus 1, it will be the application of the formula. So x sub I minus the function of x sub I multiplied by the difference of x sub I minus 1 minus the x sub I and divided by the function of x sub I minus 1 minus the function x sub I. And this will be, so you have to be careful ng ating mga parentheses. So this will be the value of our x sub I plus 1. And we're going to calculate the approximate percent relative error and the true percent relative error later. For the value of x sub I at the first iteration or simply the x sub I plus 1, so we were going to use the value of x sub I plus 1 calculated at the 0 iteration. And the function of x sub I, so we're going to use now the calculated value of x sub I at the 0 iteration as our function of x sub I. And for the function of x sub I minus 1, we're going to use the value of x sub I at the 0 iteration. And applying the formula, we will now be able to have here the value as 0.5638. And for the second iteration, so same procedure, we're going to use now the calculated x sub I plus 1 and applying or substituting the value of the new x sub I to the function and the function of x sub I minus 1, which is the function of x sub I at the first iteration and applying the formula. So we will have here this particular value. So you will notice yung pagkakapareho ng values natin ng x sub I inclined. So yun yung ating value ng x sub I and x sub I minus 1. So next is for the third iteration. So same process, we're going to use the calculated x sub I plus 1 and applying the equation to find the x sub I and finding the value of x sub I. So makikita nyo din pareho and applying the formula. And continuous lang ang ating process. So, continuing the process until the value of the function x sub I is already equal to 0. Because we're finding for the value of the root. And if it is already 0, so same, the last value of x sub I plus 1 will be the value of the root of the given function. And calculating for the approximate percent error, so we will have here x sub I plus 1 minus the current minus the previous, so divided by the current multiplied by 100, so we will have here the 63%, and same again, current minus the previous divided by the current multiplied by 100, and continue the calculation. You will have here the given until the approximation is already equal to 0. So for the true error, the true value minus the approximation or approximated value divided by the true value times 100. So, lagyan natin ang dollar sign and simply copy. So, you will have here now the result of the true percent relative error. So, this is how you apply second method using Excel. So, that would be all for our discussion for lesson 5 about roots of equations. So, thank you so much. Hope you learned our new lessons. So, have a great day ahead and always stay safe. Thank you.